That's and then I've actually inserted a little bit on trapezium systems, which I think might be interesting. And then finally, I had a choice. I was going to talk either about the evolution of disks, which is a personal interest of mine and I think very exciting, or I could give you a tutorial on measuring radial velocities, which Michael hoped would be accomplished during this meeting. I decided that you can always just give me a call and I'll tell you about measuring radial velocities, but I think this is an indulgence since that it's not necessarily directly aligned with the meeting, but I think after 7 lectures we can talk about something else. So first, just a little bit of introduction. And as with Neil, I'll give a bit of an historical tone here because I think it's actually at least very close to Kathy and my hearts. In the early 80s, when I had just got my PhD, I think you had as well, there was really an explosion in the understanding, we think, of the formation of single stars. That was when the study of disks, the famous papers by Strom et al., by Adams, Latta, and Shu, by Hartman and Kenyon were coming out. All the things that many of you now take for granted. I won't guess where you were at that time, but you probably were not thinking about these issues. And I don't think there was ever any doubt in anyone's mind that the star formation process formed binaries, because after all, we all knew from Apton-Levy that most of the stars in the field were binaries. But nonetheless, it was sort of remarkably ignored. And I would say at most star formation meetings, there was a session, and I'm sure Kathy remembers this because that's where we first met and talked many, many times. And in that session, there was almost invariably 4 talks, 1 session on binaries. And the first talk was Hans Zinnecker. And he was providing the most recent images, usually speckle images or whatever he had just recently done. I mean, Hans was sort of very eclectic about this. He would show that there were lots of interesting binaries. Then Mike Simon would often give a talk, and he was doing lunar occultation work and discovering, fortunately the moon passes right through Taurus and right through Ophiuchus, and doing really high precision resolution work. Then I would talk on spectroscopic binaries, the close binaries. And then, as I said earlier, Kathy would explain it all. And there must have, I don't know how many meetings we went to like this, but it was an incredibly exciting time because the subject that I'm about to talk about was really being discovered then. And I think every meeting that we would get together and there was something new. And then Andrea Ghez came in, finishing her thesis at Palomar, and Christoph Leinert and his group. And then the field kind of exploded. In fact, I think in my 94 review, I sort of said we were at the crux of going from the discovery phase to the more systematic study phase, which is what we've been doing since. But it was just a very, very exciting time. And I just wanted to say, Kathy, that it was an exciting time, and it was really a pleasure being together back then. And it's fun getting back together again now, since we haven't really worked together for a little while. So what we're talking about are pre-main sequence stars, broadly speaking. So I'm going to focus here really on sort of what one would call classical T-taries. I'm not going to go too massive here, 10th to 2 solar masses, both classical with accreting disks and weak-line T-tari stars, from all the way down to 1 day to upwards of 10,000 days. And as I say, really the essential finding of that period that I was talking about is that binaries are frequent among pre-main sequence objects. And in a sense, a theme that especially for the observers that I hope you'll walk away with, is that when you're modeling young stars, when you're exploring their individual properties or even the global properties of the system, don't ever forget that there's almost certainly another star there. And as I said before, with the main sequence binaries, it will greatly affect your understanding, especially if you've been steeped in the theory of forming a single star that we all, of course, teach in our courses. Unfortunately, it may have very little to do with the reality of half of your objects. So to sort of summarize where in 2008 this might have gone, there was this sense that in low-density regions like Taurus-Auriga, which of course was always a shock from the very beginning when it came in at a factor of 2 high, in Ophiuchus and other low-density associations, at least for the wider binaries, it was never so clear for the spectroscopic binaries, but at least for the wider binaries, really ever since Andrea's thesis, it was really clear that the frequency of binaries, especially the Taurus-Auriga region, but it was often generalized to all low-density regions, was a factor of 2 higher than what was in the field. The field at that time being defined by Duquesnoy and Mayor. And it wasn't really at all evident that it had anything to do with disks, whether or not it was classical T-Tauri stars or weak-line T-Tauri stars. At the same time, work in clusters, which really started out in the Orion Nebula, seemed to show that for roughly the same separations, it wasn't at all obvious that there was an increase of a factor of 2. In fact, it looked very field-like in terms of frequencies. And so this was a sense that maybe there were environmental effects in the formation of binary stars. This paper really just came out by King et al. It's a very good set of collaborators. Jenny Patience is a part of this study, and they've really done, I think, an exceptionally careful bit of analysis of the existing data, trying to really take care of same separation domains, similar dynamic ranges on getting secondaries, all the assorted systematic effects that we always knew were there, but it takes a lot of work to really analyze carefully. All that said, it should be repeated, and so I hope that some of you will. The regions that they were considering were Taurus, Chameleon, Ophiuchus, the cluster IC348, the Orion Nebula cluster. And essentially, these are 2 plots that show very similar things. This is number density of stars versus parsec cubed. So essentially, this is the environment, and this is the multiplicity fraction. And this one will suffice, although essentially the difference between these two are just separations. This is 62 to 620 AU. This is 18 to 830 AU. And the reason this has 5 and that has 3 is just because of the difference in the data sets. Their conclusion, having looked at this, is that they find very little environmental effect, except that Taurus-Auriga is strange, right? Which is the mantra for this entire meeting. IMFs, secondary mass functions, frequencies. But in particular, I think the main thing to stress here is that regions that are often lumped in with Taurus, like Chameleon and Ophiuchus, both of which are relatively low-density regions, remember this is logarithmic in scale, seem to have normal frequencies. The situation seems to be unique to Taurus, at least in this study, and the question remains why. And this number density here, the only quibble I would have, although they mention it as well, number density is a very soft, squishy thing because there's a lot of empty space in Taurus. And so to what extent these are local environments that they're considering versus global environments is an important issue.
Paul,
yeah, please.
so Taurus and Chameleon, we looked at the point in the cluster that seemed to have the most stars.
Mm-hmm.
Around there. So it's kind of a local density.
Okay, good.
And then for 348, ONC and Ophiuchus, we picked the center.
I think I was surprised that you guys got 2 orders of magnitude difference in density here. That's between.
Taurus is pretty spread out.
But in a sense, that's my point,
yeah.
Right? I mean, was your density global or was it local?
So it's local to Taurus.
Then,
I don't think it makes sense to do.
then it's not, the fact that it's spread out, in any case, it's a very nice piece of work. And I think at the moment, I would say that the issue of environmental effects remains open as a question mark. But I think we're sort of back to where we were 20 years ago at some level. It seems to be Taurus. And the question is why. This is a paper that's been referenced many times in this meeting. And honestly, I thought I had misremembered the paper. So I just want to clarify to make sure that we're all clear on what Patience et al. Said, although in fact this is work that very much needs to be done again as well. Taurus, Alpha Pair, Pleiades, Chrysope, and the field, or what's being shown here, their new data at the time was Alpha Per and Chrysope. And again, the conclusion is that at least in terms of age, these binary frequencies are not strikingly different. And again, TARS is very high. Now, of course, in the context of this paper, it was looked at as an age effect, although Jenny certainly knew that there were other regions that weren't showing this height. But the point is that TARS truly stands out as an unusual domain. These are just two figures, one from my review and then one more recent, to give a sense at least on what the period distribution, not looking at the frequency now, not the vertical scaling, just the distribution. And every indication so far over the domains that we're at, which I would say out here, the question of soft binaries remains pretty wide open from an observational point of view. But it looks like the peak in the distribution is very similar to what we see in the field. So while I grant you it's a bit of an extrapolation to go from this to a Gaussian, you could certainly imagine that this underlying distribution here is also true there. So every indication is that that period distribution is set up pretty early. And this is essentially showing the same thing. This is actually taken from a paper by Duchamp, but was building off of patients. This is the G-Dorf, Duquesnoy-Mayor distribution. These are the clusters. These are the classical T-Tauri stars. There has occasionally been mention of maybe early turnover here. Something in the wide binaries might be a little odd. Maybe this is the soft binary domain that Kathy was talking about. But I think that's a very insecure result at this point. There's still a fair amount of work to be done. Something back then that I said over and over and over again is that if you're looking for differences on samples that are inherently small, you need large numbers. And we very rarely have really had the numbers that we've needed to look for effects of anything but the very largest scale, like factors of 2. I mean, who would have thought TARS was going to come in a factor of 2 high?
Well, can I just say something about
Yeah.
very soft binaries? Because Scanny and I in 1999 looked for common proper motion pairs in Orion,
Mm-hmm.
and we didn't find any. And you can't put that down to the Jones and Walker subtracting out the mean because locally that's...
You mean within the cluster itself?
Yeah,
Mhm.
that's right. And that was surprising, and it suggested that Orion wasn't the prototype for seeding the field.
I'm curious, what did you call a common proper motion pair?
We looked at the proper motion vectors, and then we asked whether they could conceivably be bound given our estimates of the masses. Okay, so because you don't know the third dimension, but you get a limit, and we found that all the relative velocities
Right.
were larger than the escape velocity, so nothing that was projected on the sky could be bound.
I'm just surprised that the proper motion measurement errors let you do that.
Yeah, well, we certainly folded those in, but you might like to take
I'll take a look at it.
take
Yeah,
a
indeed.
bit, yeah.
Because in most of these proper motion studies, when they're talking about dispersions and the like, they're getting it out of, and this is true in old open clusters too, they're getting it out of n, right? Any given measurement is very seldom of an accuracy sufficient to really tell what direction a star is going. But when you have many of them, then you can pull it at your measurement error out of it. So all I'm saying is that I would have to look carefully to see whether I would really believe you could tell anything about 2 stars. Yeah. What you're saying about soft binaries is really intriguing. I mean, I think there's a lot of work there that could be done, and interestingly, of course, it's not technologically that difficult, right? I mean, that's not the domain a lot of people have been looking at. Did you try it statistically by any chance, just looking at whether there was an excess of wide pairs?
We didn't find anything, I'm saying.
Well, I mean, did you have a statistically significant deficiency?
Yeah,
Yes.
yeah, it was.
Oh.
But I think what you're saying, I think
Yeah.
as soon as we go out, we'll clean this up.
Of course. Michael.
On this plot, the relative frequency and period, I'm looking at the lower left, so for the CTPS, are the mass ranges over which the companions were searched as a function of separation? I mean, are all the bins fairly compared, do you think, or is there still some wiggle room there?
You mean between the figures or within the figure?
No, just on the lower left. So at each period, or I don't know what it's, I can't see what you're plotting, but I presume it's period.
Yeah, no, well, it's actually log separation, and she doesn't go down into the spectroscopic binaries. So I think this is just straight out of Andrea's study.
So they're all imaging to the same sensitivity.
That's right.
whatever Q ratio that is.
That's right. Yeah. I mean, honestly, to be very, very fair, I think you're asking the right question. I mean, Andrea did the best she could, but you know, the King-et-al. Review of the separations and the dynamic ranges, I think, has really done the job well. So that figure probably should be remade. And then I just want to point out as an aside, I'm not going to say much about it, but Hans pointed this out from the very beginning. There's a large number of higher order multiples among pre-main sequence binaries. And I'm going to talk about trapezium systems in just a second. But there is certainly a hint that there's more than you'd expect. I mean, as someone who is sort of just doing this anecdotally, I have to admit, I've looked at a lot of stars. And you know, when you're in the pre-main sequence world, it's amazing how many times, if you have a spectroscopic binary, there's a third companion there. Or if you have a close speckle, it's actually a binary that Joy noticed in 1940, right? There's a third body out there. And so the question is whether or not, how much dynamical dissolution there might be, how much dynamical evolution there might be. And of course, in groups like Taurus Auriga at fairly low density, it's not obvious whether that's an internal effect or whether it's due to external dynamical influences. I think there's actually a lot of room for study of higher order multiplicity in these pre-main sequence systems. And I actually think that there's, as Kathy's been saying in terms of wide binaries, a lot of potential for constraints on this and dynamical interactions in these systems. Now, in 2000, at the IAU meeting, I said, you know, that I thought the next discovery domain was the protostellar binaries, that is to say, embedded systems, class 1 systems. And at the time, the only one we had was L1551 from Rodriguez et al. For those of you who know the field, I mean, again, you realize L1551 is like the canonical system. That's the one where the first bipolar outflow was found. It's in the L1551 cloud. It's been studied to an inch of its life. And then lo and behold, the VLA finally came on at 7 millimeters, and it turned out to be a binary. This is an ongoing story when what I'm trying to get at is no one had considered it being a binary in all of those analyses of the system. Now, this is a protostar binary. Duchenne and Jerome Bouvier and others we're still in the discovery phase. I don't think we really have a good systemic study yet, but they've been trying to do infrared imaging on class 1 sources. And I think the main point of this slide is that even down at the protostar level, even at the, if you wish, the spherical accretion level, the highly embedded, very young systems, there's quite a bit of evidence for duplicity, for binarity, actually. Roger Griffin once said, Bob, duplicity, that means deceiving people. That's not the right word. Binarity, okay? And their main point here is simply that there, as I say, there's complementary frequencies between these two, which may sound like they should be, but remember, this phase is far shorter than this phase. So that complementarity is actually very interesting, and I suspect there is still more to be found. And then a comparison between the protostar, well, actually the total young star distribution and the field remains quite high, right? Quite much higher than the field. So the point is there's a lot of multiplicity going on in the star formation process. And the more we look, the more we find. I'm just putting this up here to be provocative. I thought it was sort of a neat idea. I don't think it has any likely physics and validity in it, but it's just something to keep in mind. They were trying to explain why Taurus Auriga was higher than young clusters, and essentially we're trying to explain it as a density effect that happened on a time scale of roughly 10 to the 6th years, both regions coming out of class 1 sources. So they were trying to look at essentially two channels as a function of density. I don't put this up here because I necessarily believe it, but just in a sense to show you how much room there is in this field for new understanding. I mean, this is probably the level of our understanding of binary evolution, young binary evolution. I'm going to skip this. We've already talked about that several times. I want to intrigue you with this one because I actually think that trapezium systems and their disruption has the potential to give us some dynamical insight on these systems. A trapezium system is not the trapezium per se. A trapezium system is an unstable, higher order, multiple system. So traditionally, and there's been a lot of classical work done on it, in order to have any stability over several orbital times, you need to have a hierarchical system. So a hierarchical triple might have roughly a ratio in separations of about a factor of 7 or more. A quadruple system will have 2 binaries, again, with a separation of a factor of 7 or more compared to the pairs. 7 just being a rule of thumb. So Hans has been pointing out since the very beginning that when you, again, not only do you see a lot of higher order multiplicity in young binaries, but many of them look unstable. Now, you have to be careful about projections here. So, I mean, you can't necessarily just take it at face value. But all 4 of these systems formally would be unstable. Now, these are in low density environments. But the trapezium, obviously, is in a high density environment. There have been a lot of dynamical studies of how long the trapezium is going to last as the trapezium. And the answer is not very long. The implications of this for dynamics are several. One is that it may actually drive dynamics. The other is that it may be a tracer of dynamics. Let me show you both examples here. This is a proper motion study of 3 radio sources near the BN object, the Beckmann-Neugebauer object. And what's interesting is that you've got high, I believe these are VLB, although I'm not sure of that, motions here, all pointing back to a locale right here. So you have 1, 2, 3, 4 sources, probably 3 objects. And the question is, was there an unstable n-body system here that went through the same kind of dynamics that Kathy was showing in her simulation and now are in the process of dispersing? Similar ideas have been put forward for runaway stars. There's sort of 2 models for runaway stars. One is the original Blau idea that you have a binary 1-star supernova and freeze the other star to run away. But the other is that you have a small n system, a trapezium type system that is unstable, goes through an interaction, and in the same way that I showed in the simulations, ejects the stars, one of which will be a massive star, and therein lies the potential for, in this case, several runaways, because remember, the mass segregation will tend to, and the encounters between binaries will tend to put the massive stars into the tight systems before they encounter each other and fly apart. So there's really right now 2 competing models that have been around for quite a while. I don't think we really understand the origin of the OB stars, but they're clearly, to my mind, a tracer of some major dynamical effect. I mean, the only way you can get these velocities is out of gravitational potential. So the question is, are they tracers of the kind of dynamics that we've been talking about? And as I say, yes, there are OB stars here. I am absolutely certain there are low mass stars doing the same thing. The question we might talk about tomorrow night is, how would you identify them? How would you know that you'd found a low mass star ejected from a young system? Well, if it kept its disk, it might be a classical T-Tauri star out in the field. There are such things. This is just a suggestion of work someone might do. This is by Helmut Abt when he entered his phase of no longer taking data and just analyzing other people's data. And I don't mean that negatively. I mean, he recognized, as the AppJ editor, what a rich resource of data there was out there. Essentially, he took a study of all trapezium regions that have been identified in the field, studied them very, very intensively to see which ones were projections and which ones were real. And what he found, interestingly, very few of them were real, most of them were projections. But those that were real, perhaps not surprisingly, all had the most massive star in the system was an OB star, rather early. And so his point is that of these trapezium systems, the oldest star in the system, in any of the systems, was a B35, which has an age of about 50 megayears or so. So his essential point was, I mean, he was trying to get a measure of the stability of these systems. But I see no reason why exactly this same approach couldn't be taken to measure the dynamical lifetimes of the regions and that we're studying, and essentially the dynamical lifetimes, not the evolutionary lifetimes, but the dynamical lifetimes of the clusters that we're working in. It's just a thought, but I'm throwing it out there for you. Okay, now my indulgence. This is a pre-main sequence star. It's a close-up. But it lacks something very, very important. It lacks a companion. This is the canonical picture of young stars, and as I say, for at least half of those stars, it's wrong. All right? Just to give you a sense of what's going on here, this is the accretion disk. This is the way Jim and Kathy modeled it. In fact, you had all this modeling in it, if I recall, didn't you? The colors and everything, wasn't that in your models? And then this is Frank Shu's, many people thought that there's a magnetospheric boundary here, essentially a barrier to the accretion, comes in through the magnetic field lines onto the star. The star is very chromospherically active and so on and so forth. Now, where this gets interesting is that when you do put a companion into a disk, it's been long known that dynamically that companion should clear, you can call it a gap or you can call it a central region, depending on the separation, as I'll show you shortly. But the Lindblad resonance from this binary is very, very effective, extremely effective, actually, at clearing out the material in the central region. And as the binary gets wider, what you end up with is really two types of disks. You end up with what we'll call a circumbinary disk. And around each star, there's a circumstellar disk. And one would be a circumprimary, one would be the circumsecondary. And they too are truncated. And indeed, one of the questions that should be going through your mind right now is that if these are accretion disks, how do these survive? Right? Take any sort of accretion rate, and unless this is a very, very wide binary and there's a lot of room here, you exhaust these in a very, very short period of time, which is the essential question. And let me just emphasize as well that not only does it clear the gaps, but it was long thought, at least, that essentially these Lindblad resonances dammed the inflow of the circumbinary material. Kathy sort of mentioned this yesterday. I loved your line, Kathy, about how accretion disks take no mass to infinity and take all the angular momentum with it. It's the same idea here, that the binary transmits angular momentum into the Lindblad resonance, which then through accretion processes carries the angular momentum out. But the material here can't cross that gap. Right? There's a balance here, essentially, between the torques being driven by the binary and the inward torques being driven by whatever process it is that drives accretion. So to give you a sense of scale of the problem, you can have very, very wide binaries. Remember I said early on, it's important that you know which scale you're talking about. If you have very wide binaries where essentially the typical disk size of, let's say, 100 AU is much smaller than the binary separation, in that case, it's quite possible that normal single star formation processes may hold true. But as you come into roughly the size of the disks, these are the stars, which are much too large, but these are the disk sizes relative to the orbit, you start getting to the point where those Lindblad resonances begin to truncate the disks. And then as you move all the way in to, say, 1 AU, now you're in a situation where a typical 100 AU disk is actually all circumbinary, and maybe or maybe not, there's small disks in here. Okay? So the scale that we're talking about is really critical. Now this one, in a sense, is my favorite. This is the one that I showed you early on, and this is my caution to you. If you go back into any of George Herbig's early papers, and you look at the list of classical T-Tauri stars, even compared to T-Tauri itself, UZ Tau East is the most active, chromospherically active, strong H-alpha, photometrically variable, infrared excess, you name it. Every parameter for a single T-Tauri that has been explained in the context of a single T-Tauri accretion disk has been used to explain and indeed parameterized based on UZ Tau East. But the reality is that this system, East and West were known all the way back to the days of Joy, But the east, that's not a cultural statement. Joy, these are called objects of joy. They were discovered by Joy in the early 40s. He knew that there were two of them here. This one, west, turns out to be a 50 AU binary, so it's sort of that middle class that I was just talking about. And a very strong accretion. H alpha of 80 angstroms is a very strong accretion disk. But UZ tau east, the classic single star T-Tauri star model, is in fact a spectroscopic binary with a separation of only 0.2 AU. And so you have a situation like this. Oh, I didn't change the yellow there, I'm sorry. This is roughly the scale size. This is 0.05 AU. So you have to picture this system with a huge circumbinary disk around it, out to 100 AU. And you have to picture accretion going on to each of these stars to provide the veiling, the chromosphere, the emission lines, the infrared excess, the mass getting onto the stars, in the context, not of a single star sitting in the center like that beautiful picture I showed in the beginning, but in the context of a very close binary, which comes within, that shark I was showing you, comes to within several hundredths of an AU every, I think in this case, 19 days. So all of you are working on single stars out there. You figure out how to get the material in onto that star. And this is just what I was showing. It is the classical T-Tauri star. It's eruptive, strong H alpha, heavily veiled, ultraviolet excess. Yeah, you can figure out what the accretion rates are. 10 to the minus 7 solar masses per year. That's a hefty T-Tauri star. Parallel spectral energy distribution, typically interpreted as a single disk. Massive disks from the sub-millimeter emission. Not entirely negligible outflow, which of course is typically driven by a single star torquing up a magnetic field and creating a columnar outflow. And a microjet. It's got everything, but it's a binary. Please.
Is there a periodicity in the H alpha?
We'll get to that. Yes. Okay. So,
Another question there.
please.
Is there any estimate of the masses of the components?
Not dynamical. From the photometry and the colors, perhaps of order 7/10 of a solar mass, something like that. Yeah. So the essential question that is the reason why I'm indulging myself here is that because this is relevant to planets too, I have to say that because then, of course, you'll be interested. Given that you have every diagnostic of circumstellar accretion in disks, how does that accreting material getting onto the star? And this star, which is one of my favorites, may or may not be the answer, although I think it's telling us a lot. This is actually a very similar binary with very similar properties. It's not quite as active as UZ tau east, but very similar properties, similar scale. And the reason it's important, well, actually, let me show you one little detail here. This is a thesis student of mine looked at the spectral energy distributions of young stars, looking for that, because a typical young star has an SED that does that, spectral energy distribution. This is the mark of a cleared gap, right there. This is that binary I was just showing you, and it actually has very little evidence for a cleared gap, okay, which is going to be important later on. So when actually a student of Gabor Basri's observed this star, they were looking for spot modulation. They were looking for rotation of spots. But quite independently of our work, they found that the brightness of it spiked regularly. Not every time. There's a few beats where it doesn't spike. But generally, the brightness spiked every, whatever the period is. God, you'd think I would know at this star. It's 16 days, 15.8 days. They found that quite independently of us. And we found that it was a 15.8-day binary. And so to get to where you were leading, every periastron, this thing flares. And if you phase it up, this may not look beautiful to those of you who work with Kepler, but that peak is quite significant and also happens in H alpha and in the veiling. In other words, in the accretion diagnostic of spectral veiling and H alpha emission, again, at periastron, it peaks. And about the same time, Pavel and Steve were finding this. Let me bring this over. This is SPH, but it's still okay. Just kidding. They found, the suspense will be killing you, I'm sure. This is a binary that actually is the same one that we discovered. We were talking to each other at least. Circumbinary disk. And what they found is that accretion streams happened. Even though all the analytic theories suggested that this material should be dammed by the resonance, in fact, what they found is when the binaries separated, it essentially opened a gate. And all of the material fell in at the same time as the binaries fell in and fell onto the stars at periastron. So these accretion streams are, certainly were not predicted by anyone, but are, if you want, the mechanism, the smoking gun by which you get from the circumbinary disk onto the surfaces of the stars. At least that's the conjecture.
Excuse me?
Yeah,
What's the black circle for the resonance location?
that's the resonance location. Yep, exactly.
So presumably that will change over time and stay.
Yep, exactly. I'd love to know what that was. That was an I bet that was an SPH comment back there. So fortunately, Willie Clay did it with a grid. And he found essentially the same phenomenon. He too modeled DQ tau specifically. And he predicted, well, I don't know if you can predict after the fact, his models showed that spikiness in the accretion rate, that spikiness that we saw as well in the binary. So these accretion streams really may be the ticket to understanding how mass accretion occurs in the formation of binary stars, and thereby the formation in most stars. So the question is, how do you actually see the stream itself? So what John Carr and Joe Najita and I did was we went to Keck to get fundamental overtone emission observations of CO. CO is a tracer of hot, dense gas, but the important thing is that it's optically thin at typical disk densities. It's thick at typical disk surface densities, so if you see it, then you know you have an optically thin region in the disk, a gap, hopefully. So we did detect it, which in itself was important. But the beauty of lines, as Kathy said the other day, is that it also gives you the ability to do a kinematic map of where the gas is. This is a cartoon figure of our discovery. And this is just showing that if you have a gap around a star, the inner region, it comes, this is where the high velocities are. So the inner region is this material right here at a higher velocity, while the outer region is in the center, and you have that classic double peak structure that you see in almost any circular edge-on or spherical edge-on system. The point is that you can use that profile to map where the gap is. And the gap is, in a sense, exactly where it should be for the companion. And there's about 10 to the minus 10th solar masses in the gap, which is optically thin, but corresponds to an accretion flow very comparable to what we see. But we still don't know if there's streams or not. Well, since we did all this, others have been looking at other stars, and UZ Tau East, that one I showed you in the beginning, it's not as striking as DQ Tau. DQ Tau is still the best case, but the solid line there is the theory of an accretion stream. The dashed lines are the photometry. The agreement's pretty good, actually. But then there's always the ones that prove you wrong. This is AK SCO. I mean, God, if any binary should have this phenomenon, it's AK SCO, because you see that strong silicate emission line there, that's an indicator of optically thin gas. I thought for sure AK SCO was going to show the phenomena, but there it is. Nature is never as easy as you think. And so essentially, what I'm introducing you to is that the possible answer, and this is essentially a dynamical problem in star formation, is the presence of a flow from the circumbinary disk onto the circumstellar disks, and as I say, roughly, or onto Jovian planets. And the idea is, how are we actually going to map out the accretion disks? And the reason I'm getting back into the field is because Gabor Basri at Lick was able to show that over orbital phases, you could see structure in the emission lines, in this case calcium-2, in that case H-alpha. But this was a lot of work. I mean, this was hard work. You had to go to the observatory many times to get a lot of spectra. But if you had an 11-meter class telescope that was Q-scheduled, not the VLT, there's never a way you could do this on the VLT, but if you had a telescope that had to be Q-scheduled because of its essential design, which means that you could only observe any object for an hour every night, but you could do it every night for a year, well, that would be perfect for this science. And so the Southern African Large Telescope is now online. It's an 11-meter telescope with a Hobby-Eberle design, a fixed altitude. And what we're basically going to do is to monitor the pre-main sequence binaries that we've been talking about in several different lines with spectropolarimetry, so we get the polarimetric information as well. And basically try to map those accretion streams in different diagnostics at different temperatures right on into the surfaces of the star. Then we take ALMA data simultaneously, and with any luck, we can actually solve the accretion problem onto binary stars, which, as I say, is half the product of star formation. So that's my indulgence, but I'm excited by this, and I know some of you are working on single stars, and I thought I'd introduce you to it at least while you were here. So that's it. Any questions on anything? Michael.
You may have said this, and I may have zoned out. The time average accretion rate, apart from the beautiful temporal signatures, what is it?
10 to the minus 7th solar masses per year.
So high.
It's so high.
All the stuff is getting through.
It's amazing, Michael. It's absolutely amazing, because all of the diagnostics are the usual ones that we always use for accretion rates. They all come from the surfaces of the stars. So you know the material is getting in there at the same rate that it would for a single star.
For the planet situation, I mean, some of us are trying to explore transition disks, as some of them could be due to planets. There's an idea that the planet could be stopping some of the stuff moving through, and so you might look at a disk mass and expecting an accretion rate, given how much stuff is there, and seeing that it's lower.
Yep.
But in this case, it's just getting in.
It's got no problem. And it really is relevant to Jovian companions as well. I mean, as you get smaller, you get to the point where the disk drives the planet instead of the planet driving the disk. But for Jovian companions, without a doubt, it's exactly the same issue. How do you get the material onto the star when you have Jupiter damming its flow? And it's,
Can I chip in on that? Because surely we want to be able to explain the transition disks to those mysterious ones which have got holes in the dust but are still heating vigorously.
Yeah.
And
But they're not vigorous. They're a factor of 10 lower than the other ones.
well, some of that 10 to minus 8, which are pretty.
Well,
Yeah.
there's this locus, if you plot the disk mass versus the accretion rate, it's a big scatter, but there's a trend. Bigger disks should be accreting at a higher rate. And then many of the transition disks lie below that by about an order of magnitude.
Although that could also be an age effect, because it takes a while for the planet to form. So on average, if you look at something that's already got a planet, it would be at a later stage of its evolution where the envelope's lower.
But for the same disk mass.
so any other questions, man? Please.
During the first days, you showed us some simulations of evolution of systems.
I'm sorry, say that again? I showed you.
A simulation of kinematics.
Yes.
And there was some binaries interacting with other stars of the system and exchange of components.
Right.
How do the disks behave in this situation? Are they gone already? Do they disappear? Are they still there? Could this be an explanation of the misalignments?
I mean, when they exchange, you mean?
If they exchange components, could this explain some misalignments? Or would the disk completely disappear in such events?
That's a really interesting question. I could speculate, but let my partner speculate first. So essentially what she's asking is if we have dynamical exchanges of stars with disks, I mean, obviously your work shows that at the level of the exchange, they'll truncate. But what happens to the disks that remain behind? Would you expect them, for example, to not be aligned because there's no reason that the stars should have aligned angular momentum vectors?
interaction.
This is the thing, there's a lot of kinematics going on during the formation process, but it's true that then later, I don't know how you want to define the end of the formation or the beginning of the kinematics, because I think they run together if we're talking about.
Yes, but I mean if it's a switch of component in the binary because of interaction with another stuff.
Yeah, so I'm saying that's
I would call that kinematics.
yes, exactly. I think that will be going on throughout the lifetime of the disk. And sure, yes,
It could be
it'll randomize the.
but it would not destroy. I mean, the disk could go on through such an event.
It truncates the disk, and then once you've truncated it, it will evolve a bit faster and go away a bit quicker. So then that becomes a quantitative question as to where it happened.
It's an interesting question, though. I mean, how long do you think it would take for the dissipation of the disks to align the angular momentum vectors?
It's about 20 orbits get roughly aligned, and then it gets much slower to get the last.
Oh,
10 degrees.
20 orbits is pretty fast.
Well,
Right.
depends on where you are, but
Yeah, but it's still, I mean, it's 20 dynamical times. That's pretty fast.
So I think this is why what's explaining in real data why more tracer systems are more aligned. I don't think it's necessarily explaining it in mapping simulations because I don't think the disks are well enough
Right.
resolved to actually follow that. But
Right. Huh. There's another question? Yes.
So you were talking about the optically thick CO lines and how you were using them.
Optically thin CO lines.
So that's the part I got confused because I didn't get the argument why you were uniquely tracing the
No.
stream region.
I understand. I sort of bumbled over that because I got it wrong when I first said it. The point is that in order to see those CO lines at Keck, we had to have an optically thin region. If you had a solid disk without a gap in it, we would never see those CO lines because if it's optically thick, we won't see them, right? I mean, they're the same temperature as the black body around them. So the fact that we saw those lines right off the bat told us we got a gap. And then we used the kinematics to map where the material is in the gap. And now we don't know it's a stream. All we know is that it's continuous throughout the gap. So I apologize. Yeah, I had it backwards when I first started.
For these really close three-main sequence binaries at periastron, can you get interactions between the magnetic fields?
Yes. You know, that's an excellent question. When we wrote the first paper, Gabor mentioned that, and frankly, I had never thought of it. But he said, you know, if these magnetic fields are big enough, those luminosity pulses might be the release of reconnection rather than any of this phenomena. So the answer is absolutely yes, and that is a subject that needs to be worked on. There's been a couple papers recently, but boy, there's a lot of work to be done on that. Yes?
I just wanted to comment that Getman 2011, I think, has a paper on DQ tau showing a large X-ray flare near periastron.
That's right. Well, it's quite possible that explains for example, the luminosity rise at periastron. There are now so many other components to the argument that it doesn't mean that's not happening, but we know we've got a cleared gap, we know we've got an accretion rate, and we know we've got material in the gap. It's quite possible that our original smoking gun that was the luminosity increase has nothing to do with it. Right? It might be the magnetic fields.
And the accretion rate that you said, the 10 to the minus 7 solar mass per year, does it come from observations or from theory?
I'm an observer. I only speak the truth. It comes from observations.